Number 1, here are a few pairs of positive numbers whose sum is 50. So sum, like you may know, means to add. So this means the total or adding. And then it asks us to find the product of each pair of numbers, which means that we need to multiply them together. So we're going to do 1 times 49, which is 49. 2 times 48, which is 96. And then 10 times 40, which is 400. Part B says, find a pair of numbers that also have a sum of 50 or add to 50 and will produce the largest possible product. So you want to come up with 2 numbers that add to 50 that will be the largest number possible. And then in C, you explain how you determine that pair. So my guess is that 25 times 25, so 25 plus 25 is 50, and then 25 times 25 is 625. That's my guess as to which one will be the largest. And then what I did after that, so I just kind of started on a guess. So my guess was that if the numbers are the same, that would be the largest. And then I checked some pairs around it. So instead of doing every number, I just started with 25 times 25. Then I was like, all right, so then let me try 24 and 26. And that was 621, so still smaller. And then I tried 23 and 27, which was, this is 621. And 24 times 26 was 624. And so you could try a couple more. And obviously, if we flipped these, if we did 26 times 24, that's still 624. Okay, and if we do 27 times 23, it doesn't matter the order you do them, you get the same products there. So the way you came to yours could have been different. You could have tried out all the pairs of numbers, or maybe not. Maybe you did something else. But this was the result. 25 times 25 gives us the largest product. Number 2, here are some lengths and widths of a rectangle whose perimeter is 20 meters. So perimeter of a rectangle, right? You add up all the sides. So we end up with 2 lengths, because we have length, and then 2 widths. So if the perimeter is 20, then the length and the width actually add to half of that, 10. So then it wants us to complete the table, and what do we notice about the areas? So when you do the area of a rectangle, you take the length times the width. So 1 times 9 is 9, 3 times 7 is 21. If the length is 5, then the width would also need to be 5, so that we get 5, 10, 15, 20 when we add them all up. And then 5 times 5 is 25. If it were 7, then the width would be 3. That's 21 when we multiply. If the length is 1, if the length is 9, the width is 1. Multiply those and we get 9. So what do you notice about the areas? You could notice some different things. I noticed that they increased, then decreased. So they started at 9, went up to 25, then started to go back down. I see that they're, kind of the same numbers repeat. So we see 9 and 9, 21 and 21, and then that 25. And maybe you see like it's a wider gap. So it starts wider, and then the gap gets narrower. So this is, a difference of 12 here down to a difference of 4. So I don't know what you want to call it. I'm going to say the gap is different. And then B says, without calculating, predict whether the area of a rectangle will be greater or less than 25 if the length is 5.25. So if we take a look at where we got the area of 25, okay, it was when the length and the width were the same. So if we go back to question number 1, the hypothesis or the guess was that this would be the largest. When the numbers were the same, then that gave us the largest product. So my guess here is that this is going to be smaller. So this is going to be less than 25. And then you could certainly check your prediction if you want to. If the length is 5.25, then the width is going to be 4.75. You could multiply those and see that they are, in fact, less than 25. C says, on the coordinate plane, plot the points for your length versus your area from the table. So we're going to be doing the length versus the area. So we're going to plot the point 1, 9. So 1, 9. And then 3 was with 21. 5 was with 25. 7 was with 21. And then 9 was with 9. And then do the values change in a linear way? So remember, linear means like a straight line if we're looking at a graph. So linear is going to be something like this, and that's no. Since they curve, right? They don't, if we connected these with a straight line and go like this, that's not where the rest of the points are. So that's a no. And then do they change in an exponential way? And that means they start like increasing slowly and then they progressively get to increasing faster, or they decrease really quickly and then it levels out. And again, neither one of those happens in this graph. So that's a no as well. Number 3, the table shows the relationship between X and Y, which are again the side lengths of a rectangle, and they show the area. Explain why the relationship between the side lengths is linear. And so in a table, what linear means is there's a constant adding or subtracting to get each value, okay? So if we plotted it on a graph, it would look like a straight line. When we look in a table, it's a constant adding or subtracting to the Y value. So as our X's each go up by 2, right? 2, 4, 6, 8, what are the Y's doing? So this is going up by 4. 8 plus 4 is 12. 12 plus 4 is 16. So these are all going up by 4. So as X increases by 2, Y increases by 4. So that makes it linear. Then part B asks us to explain why the relationship between X and the area is neither linear nor exponential. Okay, so this one versus this one. Why isn't it linear and why isn't it exponential? So again, for linear, we'll look at, is there a number that adds each time? So when we go from 8 to 32, that requires that we add 24. And when you do 32 to 72, that requires that you add 40. So we're not adding the same numbers, okay? So it's not going to be linear because we're not adding the same number to the Y or to the area. And then for exponential would mean that there's a common ratio, meaning if we divide each of the Y's, the new Y by the previous Y, there would be a common ratio. So we're going to look at 32 versus 38. So when we do 32 divided by 8, we end up with 4. And then when we do 72 divided by 32, we end up with 2.25. So the ratio, you multiply 8 by 4 to get to 32, but 32 you multiply by 2.5. So we're not multiplying by the same number. So like 32 divided by 8 does not equal 72 divided by 32. So we're not getting the same common factor there. So not exponential. Number 4, which statement best describes the relationship between a rectangle's side length and area is represented by the graph. So read these statements, which ones match the graph. So as a side length increases by 1, the area increases and then decreases by an equal amount. Well, we can see here that this area is at 18, then it goes up to 24, which is an increase of 4. Then this next one, 18 to 24 is 6. Then this next one, 24 to 28, is an increase of 4. And then 28 to 30 is an increase of 2. So this is not true. It is not, the areas are not increasing by an equal amount. Then it says in this next one that they are increasing by an equal factor. So an equal factor means dividing. So if we did 24 divided by 20, that would give us 1.2. And then if we do 28 divided by 24, we would get 1.1666 repeating. And so this is not true. It's not increasing by an equal factor either. C says, as the side length increases by 1, the area does not increase or decrease by an equal amount, which is what we just found out. So that seems to be true. But let's read D just to make sure. As the side length increases by 1, the area does not change. Well, that's not true, because the area went from 18 to 24 to 28 to 30. So the area is certainly changing. So C would be the correct answer there. Number 5, copies of books are arranged in a stack. Each copy is 2.1 centimeters thick. Complete this table. So if we have 0 books in the stack, then we're going to be at 0 for the height. If we have 1 book in the stack, okay, that book is 2.1 centimeters thick. So the stack is going to be 2.1 centimeters tall. If we add another book to the stack, now we're going to be at 4.2 centimeters tall. If we add a third book to the stack, we have another 2.1 centimeters. So that's going to be 6.3 for our total. And then if we add a fourth book, okay, we would get another 2.1. So that's going to be 8.4 centimeters. So what do you notice about the differences in the height of the stacks of books when a new copy of the book is added? So each time we added a new copy, we added 2.1 centimeters in thickness or in height. What do you notice about the factor by which the height is changing? So when we're looking at the factor here, that's dividing these. So, or what do you multiply by to go to the next one? Well, you can't multiply 0 by anything to get to 2.1 because 0 times anything is 0. So this one doesn't exist. If we go from 2.1 to 4.2, so you can just divide 4.2 by 2.1. This increases by a factor of 2. If we want to figure out this one, we can do 6.3 divided by 4.2. And when we do that, we end up with a factor of 1.5. And if we wanted to similarly find this one, we could do 8.4 divided by 6.3. And get 1.33 repeating. So the factor as the book is added is actually decreasing. So the factor is decreasing. How high is a stack of books if we put B books? in. So if we did B books, right, what were we doing every time we added a book is we were adding another 2.1 here, right? So if we had B books, we would be doing 2.1 plus 2.1 plus 2.1 up until we had a total of B times that we added, right? And that's the definition of multiplication. So we would have 2.1 times whatever B is, however many times we needed to add 2.1 together. So 2.1 times B. Number 6, the value of a phone when it was purchased is $500. It loses 1/5 of its value each year. What is the value of the phone after 1 year, 2 years, and 3 years? So to me, I don't like to do it with loses its value. You certainly can. You just have, this just makes you do it in 2 steps. So if you take what's 1/5 of 500, you end up getting 100 for that. Okay, so that means it's going to lose $100 of its value in that first year. So then when you want to figure out what the actual value of the phone is, you have to take the original cost and then subtract off that lost cost. And that gives you $400 for that first year. So that's one way to do it. Okay, I don't personally like to do it that way. If we talk about losing by 1/5, then I like to talk about what I keep. Okay, so the value that I would keep if 1 out of 5 parts is lost, 4 out of 5 parts is kept. So I could also just do $500 times 4/5 and get directly to my new value of 400. Then you could do that again for 2 years. So now in the second year, the phone is worth $400 and it's going to keep 4/5 of its value by the end of that year. And when we multiply 400 times 4/5, we end up with $320 as its value after 2 years. Then in the third year, it starts at $320 and then it's going to keep 4/5 of its value. So we'll multiply by 4/5 and we end up with it being worth $256 at the end of that third year. So then Tyler says that the value of the phone decreases by $100 each year since 1/5 of 500 is 100, which we agree with. We talked about that here. 1/5 of 500 is 100. So then Tyler's saying then we're just going to subtract 100 from the phone each year. Do we agree with Tyler or disagree? And so we disagree, okay, because it's going to lose 1/5 of its value the first year. So then it's going to be at 400 when it starts the next year. And so it loses 1/5 of its value each year. So you have to repeat using the previous year's value. So it goes down in value to 400. And then 1/5 of 400 is no longer 500. So you have to take 1/5 of the new value each year. Not just 1/5 of its original value. All right, number 7 requires some technology here. And so you need to be able to write a line of best fit or plot some data. So the data in the table represents the price of 1 gallon of milk in different years. And then I missed a direction here, but it says to use graphing technology to create a scatter plot. So I'm going to use my graphing calculator here. If you don't have a graphing calculator, you can get this app on your phone for free. On an iPhone, I believe on an Android as well. So you could download that. It's called Calculate 84, I believe. Let me check. Yeah, Calculate 84. Let me write that down. Is the calculator app. So that's the calculator app if you need that. You should also be able to do this on websites like Desmos. But if you have the graphing calculator, you are going to go into Stat, and then you're going to select option number 1, which is edit. And then you're going to type this data in. You can see I already have it typed in here. I am going to delete one of the rows so I can show you how to type it in. And so if you need to clear out this data, you do not want to click delete. Okay, it'll delete your entire row so that you can't enter data anymore. So instead, you want to arrow up on top of the L1 and you want to push clear. Then when you push the down arrow, you'll notice nothing happened here, but it cleared out the whole list here. So when you click down, all of that data will be gone. And so you just want to clear out the data and then type in the data for this problem. And you just want to be very careful as you're typing in the data to make sure that you are typing it in accurately, because if you don't type it in accurately, you can't get the correct answer. So just make sure every time you enter a number, you look at it to make sure that it's correct. And then as you type in the price, make sure that it lines up with your years. Okay, so once you get the data in, again, just make sure that these match like they're supposed to, because if they don't, then you won't be able to get the correct data. So now when you go to actually plot these values, okay, you want to go into stat plot. So on mine, you can maybe see that it's blue right here above the y equals. So you click the second button and then the y equals button to get into your stat plots. And then you're going to want to turn it on. Mine is already on, but you would click in it. So you'd hit enter and you'd click it. So yours is probably off like this. So then you want to be on and you want to click enter so that that's highlighted. Select the graph you want. We want a stat plot. So we just want a scatter plot here. So we're just going to keep it on this first one. I want list 1 to be my X's, list 2 to be my Y's, and then you can pick the type of dot that you want. So I'm just going to leave it at this. Then you're going to go into zoom, because most likely your graph looks like this. So if you hit graph, it'll look like this. So you're going to want to go into zoom and you want to actually zoom in on the data. So there's an option called zoom stat. And zoom stat means that your window will zoom in on the statistics that you just typed in. So select zoom number 9, and you can either arrow down to 9 or just hit the number 9. And then, oh, it looks like I have a data point that's off. So I must have typed something in wrong while I was talking. So let's go back into my list. So stat and edit and look for what year is off. Oh, there it is. So 198 instead of 1980. So then fix that and then go back to zoom number 9 or zoom stat, and then my data looks better. So now you can use this and it says, does a linear model seem appropriate for this data? Why or why not? So does it look like this is kind of in a straight line? And yeah, it does. It's not in a perfect straight line, but it looks pretty linear. Okay, everything seems to be increasing pretty steadily as we move over time. And so then you can say that here. And I'm just going to call it a straight-ish line, right? You can say, because it seems to be increasing at a constant or a pretty constant rate or whatever, I'm just going to say it looks to be a straight-ish line. So now it says, if our data seems appropriate, create a line of best fit and round it to 2 decimal places. So the way we use our calculator to do line of best fit is we go back into the stat menu. Okay, so click on stat. Then you want to go over to calculate. So you want to move over to calculate. And then linear regression is another word for line of best fit. So then we want to pick this option number 4. And then you might have some stuff on your screen here. It just re-asks you if you want what you want the x's to be list 1, y's to be list 2, and then it says calculate down here. If you don't have this screen, don't worry, just push enter, or you might just have your information already on there. So now here's our data. So I'm just going to screen grab this. And then I'm going to paste it over here so we can look at it. So this is our line of best fit, but we have to still write it. So it gives us the template up here. So we see that it says that we're going to be doing y equals ax plus b. So the a here is this number. And so we're going to plug it in. And then the b is this number. And then we're going to plug that in. So we're going to go y equals, and then we're going to put that a number, and it wants it rounded to 2 decimal places. So I'm just going to put 0.0, and it says 35 here, so that rounds it up to 4. And then we'll put x, and then plus the b value, which is negative 67.44. And you can leave this as plus negative 67.44, or you could have just put a subtraction. But there's your line of best fit. So then it says, what does the slope of this graph mean? And the slope is the number that's always in front of the variable. So the slope is our a value in this case, and it's 0.04. So it means that the milk is increasing $0.04, meaning 4 cents per year. And is that realistic? Yeah, it appears to be going up by about 4 cents, right? So this is 5 years, so that's about 20-cent growth. 5 years, about 20 cents. But so yes, this is reasonable. Then it asks us what the y-intercept of the graph is. And the y-intercept of the graph is that constant number. So in this case, the negative 67.44. So what does this mean in context? So y-intercept would be 0, negative 67.44. This means that in year 0, milk cost negative $67.44. So does that make any sense? No. Because what does negative 67.44 actually mean for a cost? It means that the store would pay you $67 to take the milk from them. So you'd walk into the store, they'd be like, if you take this milk, we'll give you $67.44. That's not reasonable. Okay. So no, the cost can't be negative. All right, then number 8 says, give a value for R, your correlation coefficient, that indicates that a line of best fit has a negative slope and models the data well. So remember that your R values go between -1 and 1. And the closer they are to 1 or -1, the better they fit the data. And so if it's a negative slope, it's going to be close to -1 if it's fitting it well. And so in this case, we want something close to -1. So maybe like negative 0.98. That would be really good. Okay. You could have something like negative 0.9. You could have negative 0.83. Really anything that's negative 0.8 or higher, negative 0.8 or closer to -1 would be fine.